Hello everyone, I'm Jyun Liao, and today we're going to talk about optimal error pseudo-distributions for reward expansion programs. And this is a joint work with Ishan Chattopadhyay. The motivating problem for this work is the BPO versus L problem. A major open problem in complexity theory is, does randomness help in space-bounded computation? And formally, we wonder if, given the problem solvable by a randomized algorithm in space S, is it always possible to solve the problem deterministically in space linear in S? And by a standard padding argument, we know that it suffices to solve the case S equals to log n. So this problem is equivalent to asking, is BPO equals to L? So the formal definition of BPO is, we say a language L is in BPO if there exists a randomized log space polytime algorithm A such that the algorithm will output the correct answer with probability at least 2/3. And there is also a one-sided error version called RL, where the algorithm will always output correctly if the input is a no instance. And the usual way to model this randomized space-bounded computation is by a Riemann expansion programs. So Riemann expansion program is a graph with n layers, and in each layer there are at most W nodes, where W is called the width of this expansion program. And from each node there are two edges with a label 1 and 0 respectively. And this expansion program can compute a Boolean function as follows. So given an input, first we will start from the starting node and following the edges with labels equivalent to the given input. And we will decide whether to output 1 or 0, depending on whether we reach the accept node in the last layer. And this can be used to model a non-uniform randomized space-bounded computation by first fixing the input of the randomized algorithm and consider the function, consider the mapping from the random coins to the output of the algorithm. So given the space S algorithm, we will construct the Riemann expansion program with length n equals to the number of time steps, and the width W equals to 2 to the S, because there are at most 2 to the S possible memory configurations in the algorithm. And in the log space setting, which we care about, W, the width will equals to poly n. And note that the expected value of this function f is equivalent to the accepting probability of the algorithm. So if we are able to compute or even approximate this expected value, then we will be able to distinguish a yes instance from a no instance in the BPO language. And similarly, this is also true for RL. And a natural way to approximate this expectation is via a pseudorandom generators. So a pseudorandom generators will take the bits of random coins and extend it to n bit of fake coins. And given the pseudorandom generator G, if we compute the expected value of a Riemann expansion program on these fake coins, we will it is guaranteed that we will get a good approximation of the actual expectation of f. And ideally, we will want D to be log n so that we can enumerate all the possible input of G in log space and compute a good approximation of the expectation to randomize BPL. And if we only want to randomize RL, then a weaker object called a hidden set generator is enough. And in a hidden set generator, we only need the condition that if the expected value of the function f is larger than epsilon, then it will imply that at least one output of the generator will be accepted by the function f. And previously, it is well known that there exists a non-constructive PRG with C length log nW over epsilon. And note that in the setting we care about, the width W equals to poly n. And so if there exists an explicit PRG with such C length, then we will be able to derandomize BPL in log space. However, the best non-explicit PRG by Nisan in 1990 has a C length which has an extra log n factor compared to the optimal non-constructive PRG. And this will only imply that BPL is contained in log square. And although Nisan discovered this result 30 years ago, and there are also many other works in some restricted settings, Nisan's generator remains the state-of-the-art PRG for real expansion program in the general setting, even for with 4. But recently, there is a surprising result by Braverman, Cohen, and Garg showing that if we only need a hidden set generator, then we can actually remove the log n factor from the log 1 by epsilon term. And a later work by Hoza and Zuckerman showed that they can further remove the log factor from the BCG paper. And Hoza and Zuckerman use a very beautiful construction, which only requires 2 pages to prove. However, the original work by BCG still has the advantage that they actually construct the pseudorandom pseudo-distribution, which is a stronger object than a hidden set generator. And while the Hoza-Zuckerman result is restricted for a hidden set generator. So a pseudorandom pseudo-distribution is actually pretty similar to a PRG. But in a PRG, we are approximating the expectation of F by computing the average of F on the generator outputs. And because we are able to approximate the expectation, so we can derandomize BPL. But in a pseudorandom pseudo-distribution, the difference is the output of the generator can not only contribute positively to the approximation, but it can also contribute negatively to the approximation. And we will need another function rule to compute this signed weight. And with the pseudorandom pseudo-distribution, we can also approximate the expectation of F. So this is also suitable for derandomizing BPL, which is stronger than a hidden set generator, which is only for RL. And obviously, a PRG will imply a pseudorandom pseudo-distribution by taking the weight rho to be 1. And Braverman, Cohen, and Garg observed that in a pseudorandom pseudo-distribution, the generator G is also a hidden set generator. And the main result in this work is we construct an explicit PRPD with C length which is optimal for a small error. And compared to the result of BCG, we further remove a log factor from the epsilon term. And we also believe that our construction and analysis are simpler than the original work in BCG. And this is a comparison of our work and the previous work. And before we go into our construction, first, we briefly explain why we care about the small error setting. So in 1995, in a seminal paper by Sachs and Zhou, they show that BPL is actually contained in log to the 1.5 place. And this is still the state-of-the-art derandomization for BPL. And in this work, they use Nisan's generator for epsilon equals to 2 to the minus log square n, which is the small error setting we care about in this paper. And Braverman, Cohen, and Garg further show that if there exists a PRG with C length log square n plus log W over epsilon, which means if we can further remove the log m factor from this log w term, then following such and those scheme, this will further imply that BPL is contained in log to the 4/3 space. And in our paper, we show that a Pseudorandom pseudodistribution with the same C length suffices if there is a bound on the a poly NW over epsilon bound on the weight of this PRPD. So now, first we briefly review the matrix view of a Riemann expansion program. So given with W Riemann expansion program, first we consider the transition from the first layer to the second layer. And so we will get two matrices corresponding to the transition matrix following edge with label 1, or the transition matrix following edge with label 0. And similarly, we can construct matrices in the second and the third and fourth layers. And so these matrices together will fully encode this Riemann expansion program. For example, given the input 1011, and if we only consider the transition matrix corresponding to this input, and we take the product of these matrices, we will actually get the transition matrix from the first layer to the last layer. And to compute the output of this Riemann expansion program, we can first consider the row corresponding to the starting node, and then the column corresponding to the accepting node. And this crossing entry will be the output of the Riemann expansion program. So given this matrix view, we can actually interpret a PRG as a matrix. So recall that for a PRG, we want to compute a function G, a generator G, such that f on the expected value of f on the generator output is epsilon close to the actual expectation of f. And if we replace this f with the transition matrix of the ROBP, then our goal becomes that we want to compute a matrix M prime, which is only the average of 2-3D transition matrix, such that this matrix M prime is the epsilon approximation of the random walk matrix. And here we say the C length of M prime is D. And similarly for PRPD, we can also take M prime to be the weighted average of some transition matrices. So with this matrix view, now we are ready to introduce Nisan's generator. And Nisan's generator, in Nisan's generator, we want to compute the random walk matrix. And the first step is we will decompose this matrix into two halves. So the random walk matrix can be expressed as a product of the random walk matrix of the first half and the random walk matrix in the second half. And we can compute, we can do this decomposition recursively. So we will get a binary recursion tree with log n levels. Now suppose that we have the approximation of the left random walk matrix, which is A, and also a good approximation of the right random walk matrix. And if we compute the product AB, then this AB will also be a good approximation of the random walk matrix of the whole program by triangle inequality. However, if both A and B take d bits, then AB will require 2d bits to implement. And because we have log n level of recursion, so this factor 2 is too large. So the idea of Nisan's generator is to further approximate this matrix AB with another matrix tilde AB, which only have C length D plus T, which is only T bit larger than each side. So if we can do this in each level of recursion, then the C length of the generator will be log n times T. And later we will see that this T is log NW over epsilon. So now we focus on the how to approximate the matrix product. Now suppose given we are given a matrix A, which is the average of some matrix AX, and also B, which is the average of some matrices BY. And what we want to do is we want to find some pairing XBY such that the average of these XBY is a good approximation of AB. So of course, the naive way to do this is we consider all the possible pairing of XBY and compute the average. And this will be exactly the product of A and B. But as we have seen in the previous slides, this product has C length 2m. And this factor 2 is too large for the binary tree recursion. So instead, in Nisan's paper, he replaced, he get this pairing by applying a pseudorandom graph. So previously, the pairing of all possible X and BY can be viewed as a complete graph. And here, instead of using a complete graph, Nisan used a pseudorandom graph with degree only poly NW over epsilon. And this pseudorandom graph is a pairwise independent hash function in Nisan's original work. And in some following works, it can be also, we can also use expander or extractor or sampler for this pseudorandom graph, and all of them work. So now the C length of this sparsified product is only log NW over epsilon larger than each side. So therefore, the C length of Nisan generator will be log n times log NW over epsilon. But in this construction, we are paying this log 1 over epsilon term in each level of recursion. So the idea of BCG is to try to amortize this log 1 over epsilon term among all the level of recursions. And we will also follow this similar idea of BCG. So to achieve this, we need to compute this sparsified matrix product with an averaging sampler. So an averaging sampler is a function which takes n bits of input and d bits of seed and compute the n bit output. And this can also be viewed as a bipartite graph, where the left-hand side has 2 to the n nodes, and the left degree is 2 to the d, and the right-hand side has 2 to the m nodes. And we say this bipartite graph is an averaging sampler if for every function which maps the right-hand side to a Boolean value, and it satisfies the fact that for most of the node X on the left-hand side, if we take the average value on the neighbors of X, then we will get the epsilon approximation of the actual expectation of F. And this will be true for most of the X, except for only a delta fraction of them. And it is not hard to prove that this is also true for a matrix value function if the output matrix has some bound on the entries. So now we show that we can actually apply the sparsified product with this sampler by placing AX on the left-hand side of this graph and BY on the right-hand side of this graph. So to prove this, recall that for by definition, for most of the X, the expectation of B on its neighbors will be epsilon close to the actual expectation of B. Therefore, this is still true after we multiply it with the matrix AX on the left-hand side. So this means after we take the average of this on all the X, we will get that the left-hand side will be the sparsified product and the right-hand side will be AB, which means the sparsify product is close to AB. And the error will be epsilon plus delta, which comes from two parts. So the first part, epsilon, comes from the good X, which satisfies the approximation stated above. And the delta comes from the bad X, which doesn't satisfy this approximation. But because there are only delta fraction of them, so this only contributes a delta term to the error. And the main observation in BCG is they observe that this epsilon term in the error is actually scaled with the norm of the matrix on the left-hand side. So and note that we can get the averaging sampler with the parameter listed on the slide. And the C-length of the product will be n plus d, which is d bits larger than the left-hand side. And if we have matrices such that the AX has a very small norm, then that means we don't need the epsilon to be as small as the case that AX doesn't have small norm. So now know that this epsilon is the dominating term in the C length D, in the increase of C length D. Therefore, the increase of C length will be short if the AX has small norm. But however, we cannot directly apply this in Nisan's generator because in Nisan's generator, all the matrices are stochastic, which has norm 1. So this observation doesn't really help. So the idea of BCG to actually benefit from this observation is that every time when they compute the product of two matrices, they actually compute this product as the telescoping sum like this. So they will write A to be a rough approximation AG plus the error correction term A2G minus AG and so on. So the first term will be a rough approximation, and the following terms will all be small norm matrices. So with these small norm matrices, we can apply the observation in the sampler trick mentioned in the previous slides. So, and they will maintain the invariant that for every term which has 2 to the minus k norm, the C length is roughly only linear in k. And because we only want the epsilon approximation, so we can discard all the terms with norm smaller than epsilon. And this will imply that the C length is roughly log 1 over epsilon. But although their idea is pretty clean, because this idea has a bottom-up nature such that every time we apply a sparsified product, we need to do this telescoping sum trick. So there will be many small terms which make the setting of parameter sort of complicated. And there are also some special case treatment required in their original construction. So to simplify this construction, we take a closer look at what is needed in this sampler trick. So the first property required in this sampler trick is that if we are compute the product of two matrices where the left matrix has a long C length, then we want it to have a small matrix norm. Because the C length of the sparsified product will be n plus d, where n is the C length of the left-hand side. And if we have the property that the left-hand side actually have a small norm, then this will imply that we can actually assign a larger epsilon to get the error we want. And this will imply that d is shorter because d is dominated by this log 1 over epsilon term. And the second property we required by this sampler trick is there need to have a short C length on the output side of sampler, because in a sampler it is required that the input side is larger than the output side by a Lagrange delta additive term. And we can see that this delta doesn't scale with the matrix norm on the left-hand side. So this means we need to make sure that the m is much shorter than n, so that this inequality is satisfied, and that this log 1 over delta term will not harm the final C length of our construction. So with these two properties in mind, we use two main technical lemmas to get a simplified construction. And the first one is instead of using the bottom-up telescoping sum trick as in BCG, we replace it with the top-down recursive formula. So we apply a recursive formula as follows. So first, suppose, so here as in Nisan's generator, we cut a Riemann spectrum program into two halves, and we consider A as a random walk matrix of the left half, and B as a random walk matrix of the right half. And our goal is to compute approximation of the product AB. And now suppose AI is gamma to the I+1 approximation of A, and similarly for BI, then we will compute a good approximation of AB using this recursive formula. And note that this recursive formula also have a negative sign inside, which makes our generators pseudorandom pseudodistribution. So we will also maintain the invariant that for these like AI, BI, CK, if they are a 2 to e minus k approximation of some random walk matrix, then it also has roughly linear in k C length, so that our final construction has C length roughly log 1 over epsilon. And the proof of this recursive formula is also not very hard, because if we consider the difference between this recursive formula and the actual product AB, then we can actually decompose this into the sum of some small term. And here we write it down, and we can see that each term has norm at most gamma to the k+1. And also, this recursive formula will satisfy the property we mentioned, which is required for to apply the sampler trick in BCG. The first property is for given a matrix with a larger C length, it needs to contribute a smaller matrix norm, so that we don't need the epsilon to be too small, and the degree of the sampler can be smaller. So this is true in our construction, because given a larger C length AI, we will get a small matrix. We will get a small norm matrix AI minus A. And the second property is also true, because observe that we only consider the product AIBJ such that I plus J is smaller than K, so that it is guaranteed that either AI or BJ will have a small C length. So this satisfies the second property required for the sampler trick. And note that unlike in BCG, they construct the small norm matrix explicitly, but here the A and B here only appear in the analysis, so our small norm matrix is kind of implicit. And the second idea we use to simplify the construction and also improve C length is an idea called flattening. So recall that in the sparsified product, we consider a biproduct graph where in each node there is a transition matrix inside. But to apply a sampler trick, unlike in Nisan's generator, where each node only contains a transition matrix from the first layer to the last layer, in the sampler trick, we actually need each node to contain weighted sum of some transition matrix. And in this form, there will be two parts. The seed of this structure actually consists of two parts. The first part is the outer seed, which is correspond to the number of nodes, and this part is recyclable via a sampler. But the second part is the inner seed, which is the seed required to implement the matrix inside each node, and this part is not recyclable. And we need this because we need the node-wise matrix norm to be small. But the new observation in our paper is this kind of node-wise small norm matrix is not required for the output side of the sampler. So every time when we are applying a sparsified product using a sampler, if for the matrix on the output side, we can actually flatten these nodes to, like for example, if in a node, there are like K matrix to implement the matrix inside this node, we will flatten it into K separating nodes, so that the inner seed now becomes the outer seed, which is recyclable. And although this flattening trick will increase the outer seed, but because we only apply this on the output side, so this is not actually not too harmful, because the output side always have a shorter seed length. Yeah, so this is our construction, and now there are some open problems left from our paper. So the first problem is whether we can construct a PRG with optimal error dependence. And I think this is related to the question that whether a negative weight is required in this sampler argument from BCG. And in the original paper of BCG, it seems kind of necessary because we need to take the difference to get a small norm matrix. And in our paper, our small norm matrix now become implicit, but we still need the negative sign to guarantee that the output side has a small C length. So we are not sure whether this negative weight is actually required to apply this trick. And second open problem is to construct a PRPD with log W over epsilon C length when the branching program is very short, where the length is about 0.0 log W. And note that such C length is achieved in the paper by Hozai and Zuckerman, but their technique is restricted for the hidden set generator. And we think a possible approach is to apply the technique in this paper using the square root log W, using a recursion tree with square root log W branches, as in Nisan Zuckerman. But because the inner seed we mentioned in the previous slide cannot be recycled, so if we use a recursion tree with more branches, the inner seed will also be multiplied by the factor, which equals to the number of branches. And the inner seed actually contains a log W term. So this makes the output seed much worse than what we want. And finally, the important problem is to get a PRPD with C length log square n plus log W over epsilon. And if we can get such PRPD explicitly, then this will imply that BPL is containing log to the 4/3. Okay, thank you for listening.